It began with a sound. A low hum that grew into a roar, the pulse of 1,000 engines carving through the clouds above Europe. It was 1944. The air over France trembled with the rhythm of flight, silver wings flashing, propellers cutting the sunlight into spinning halos. To the men on the ground, it was the sound of hope. To those in the air, it was the sound of survival. But hidden inside that deafening thunder was a secret, a mechanical whisper that changed everything. A single invention, born in the mind of an American engineer years before the war began, had quietly made these aircraft almost 100 miles per hour faster. It turned good planes into legends and pilots into heroes. Yet few would ever know his name. This is the untold story of Frank W. Caldwell, the man who gave machines the power to think, and whose impossible propeller helped win the skies of World War II. And if stories like this fascinate you, stay with us until the end. There's more to this war than gunfire and courage. There's the genius of one quiet mind that changed the fate of the air. In the early 1930s, aviation was still finding its wings. The Great War had proven that flight could decide battles, but peacetime had revealed its limits. Engines grew stronger, sleeker, more powerful. Yet the propellers, those spinning blades meant to convert that power into speed, had hardly evolved at all. Fixed-pitch propellers ruled the skies. Their angle was set before takeoff, meaning they could perform efficiently at only one speed. Too steep, and the engine struggled to push forward. Too flat, and it over-revved, burning itself out. Every flight was a compromise. Pilots knew it, engineers hated it, and Frank Caldwell refused to accept it. At Hamilton Standard, a small division of United Aircraft in Connecticut, Caldwell was already known for precision bordering on obsession. He wasn't loud nor charismatic, but he had a way of asking questions that made others uncomfortable. What if the propeller could adjust itself? He once asked a colleague. Adjust itself? Came the reply. You mean fly on its own? In a way, yes, Caldwell said quietly. Why shouldn't it? That question became his life's work. He imagined a system where the propeller could automatically change its blade angle as airspeed or engine load shifted, keeping the engine turning at a constant, efficient speed. In theory it was perfect. In practice it seemed insane. To make such a device, one needed a mechanism that could sense and respond to engine speed, instantly, without any pilot input or electronics. Only gears, oil, and physics. Colleagues dismissed him. Some laughed. You're building a clock for a hurricane, one said. But Caldwell persisted. He spent nights at the drafting table, sketching designs for a hydraulic governor that used centrifugal force to alter blade pitch. The faster the engine spun, the governor's counterweights pushed oil through valves, twisting the propeller blades to reduce load, automatically holding engine revolutions steady. It was breathtakingly elegant. It was also impossible to perfect. For months, prototypes seized up or leaked under pressure. One test ended with a blade detaching mid-flight and embedding itself in a nearby field. Another shattered under vibration, scattering metal across the runway. Each failure drew ridicule. But every explosion, every fracture, gave Caldwell another data point. He recorded everything: oil viscosity, blade flex, stress tolerances, chasing harmony between metal and air. He wasn't simply solving a problem. He was teaching a machine to adapt. In those years, America's aircraft industry was small and cautious. Air travel was for the rich, and the military had little appetite for experimental mechanics. Caldwell's project was tolerated, not celebrated. He received small budgets, limited manpower, and even less faith. Still, by 1933 his system began to work. The latest prototype, heavy, awkward, but functional, adjusted its pitch automatically during engine tests. On the ground, engineers watched in silence as the propeller held steady revolutions while throttle and load changed. The impossible had started to breathe. In 1934, the first airborne test took place on a WW2 Corsair, an old biplane that had seen better days. Pilots were warned it might fail catastrophically. But when the aircraft climbed into the sky, the governor hummed smoothly. The engine maintained perfect speed. It climbed faster. It cruised farther. It landed with the same calm hum it had left with. For the first time in aviation history, a plane had managed its own power. Word spread quickly, not across newspapers but through engineering circles. Competitors like Curtiss and de Havilland began developing their own systems, most relying on manual or semi-automatic controls. but none were as seamless, as instinctive as Caldwell's. Yet recognition eluded him. When the National Advisory Committee for Aeronautics reviewed his work, one senior engineer called it a delicate toy unsuited for military stress. It was the curse of innovation. To be too early is to be invisible. But Caldwell was patient. He wasn't chasing fame, he was chasing perfection. He refined the mechanism again and again, trimming weight, simplifying maintenance, improving the balance between hydraulic pressure and centrifugal force. He tested hundreds of oil types, searching for one that would not seize in freezing air or leak in the tropics. By 1938, the U.S. Army Air Corps was watching closely. Pilots were now pushing their planes faster than ever, and fixed-pitch propellers were reaching their limits. Overheating engines, lost fuel efficiency, shattered gearboxes, the same problems Caldwell had foreseen years before, were crippling progress. So when his constant-speed propeller demonstrated a full 25% improvement in climb rate and nearly 100 miles per hour more top speed, the military finally took notice. Contracts followed. Hamilton's Standard ramped up production. Suddenly, Caldwell's toy was being fitted to fighters, bombers, and transports across the country. But still, doubt lingered. Could a machine that delicate survive the violence of war? Only one way to know. In 1939, Europe erupted. German Stukas screamed across Poland. Spitfires clawed through British skies. America watched, wary, but its engineers were already preparing. Every new aircraft rolling off American assembly lines, the P-40 Warhawk, the B-17 Flying Fortress, carried Hamilton's Standard propellers at their core. Caldwell's system was no longer a theory. It was a heartbeat. But he didn't celebrate. He knew war would be the true test, not of design but of endurance. If his propellers failed in combat, they wouldn't just tarnish his name. They'd cost lives. He pushed his team harder. Every screw, every bearing, every seal had to be perfect. He knew that perfection was the only kind of mercy an engineer could give to those who flew. In late 1940, during field tests in Arizona, the Air Corps confirmed what Caldwell already believed. His constant speed system wasn't just efficient, it was transformative. Planes flew farther, faster, and with less strain on their engines. Maintenance times dropped, mission range expanded, and pilots began to describe something new, a sense of calm, as if the machine itself had learned to breathe. Still, history moves slowly for dreamers. Recognition was postponed. Credit was shared. And as nations prepared for war, Caldwell simply continued his quiet work, knowing that the truest victories are the ones no one sees. Because in a few short years, his invention would do more than change flight. It would change the outcome of the greatest conflict in human history. But in 1939, as storm clouds gathered over Europe and the skies darkened with wings, Frank Caldwell could not have known what was coming, that his impossible idea, born from equations and stubborn faith, would soon become the most powerful secret in the air. And above all, he could not have imagined that his quiet revolution would turn into the very sound of victory. By 1939, war had swallowed Europe whole. Across the Atlantic, America was still a nation of cautious optimism, building weapons for a war it claimed it would never fight. But behind the slogans of peace and neutrality, a quiet transformation had already begun. In factories from Connecticut to California, the hum of machinery filled the air. Engineers worked through the night, guided not by orders from generals but by the ticking urgency of time. They knew that when the United States finally entered the conflict, it could not afford to be unprepared. And at the center of that preparation was a propeller, a small piece of metal in motion that had already begun rewriting the laws of flight. Hamilton Standard's new constant-speed propeller was now standard equipment on almost every American aircraft in production. But few outside the industry understood what it really meant. To the untrained eye, it was nothing more than a spinning blur of aluminum. To the pilot in the cockpit, it was a new kind of power, precise, dependable, and alive. For decades, flight had been a struggle between man and machine. Pilots were forced to balance the throttle, mixture, and pitch with constant attention. The slightest mistake could cause an engine to overheat or stall. But now, something extraordinary had happened. The propeller managed itself. It adjusted to air resistance automatically, keeping the engine at its most efficient speed. The effect was almost supernatural. Pilots described it as flying with an invisible co-pilot, one that anticipated every movement before they did. Still, the military didn't trust miracles. When the first series of combat tests began in late 1939, skepticism was thick as engine oil. Pilots and mechanics gathered around the Curtiss P-36 fighters lined up on a desert runway in Arizona. Each was equipped with Caldwell's propeller system. The air shimmered with heat as the engines roared to life. The propellers spun faster and faster, then leveled into a smooth, steady hum. No overspeeding. No vibration. The aircraft leapt from the ground, climbing with a precision that stunned even the most experienced flyers. Observers recorded the numbers: climb rates up by nearly 30%. Range extended by more than 15. Top speed increased by over 80 miles per hour. The impossible had become undeniable. Reports poured in from test fields across the country. Pilots used words rarely found in engineering memos: smooth, balanced, effortless. Caldwell read every one of them. He didn't smile, he simply nodded, made notes, and went back to work. He knew this was only the beginning. As Europe fell deeper into chaos, Hamilton Standard's engineers worked under floodlights, machining propeller hubs from solid billets of steel, each one destined for an aircraft that hadn't yet taken flight. Caldwell walked the factory floors quietly, running his hand over crates marked with serial numbers and destinations. He had built something elegant, and now it was about to be tested by the ugliest thing humanity had ever created. By 1940, Britain was fighting alone. The Luftwaffe ruled the skies over France, and now it turned its attention to the British Isles. The Battle of Britain had begun. While the Royal Air Force scrambled to defend its homeland, American observers watched closely. They studied every dogfight, every burned-out engine, every shattered airframe. They learned one devastating truth: control was everything. At high altitudes, pilots had to choose between engine safety and survival. The manual pitch systems used by British fighters required constant adjustment. Many pilots, overwhelmed by the speed of combat, misjudged and destroyed their own engines. That lesson would shape the future of American aviation. By early 1941, the U.S. Army Air Corps ordered every frontline aircraft to be fitted with Hamilton Standard's constant speed system. The contract was staggering: hundreds of thousands of units, each built to tolerances finer than the width of a human hair. In the hangars of Hamilton's Connecticut plant, men and women worked side by side, assembling the devices that would soon define air superiority. Some had never even flown in a plane. They didn't need to. They understood that what they built could decide the war long before the first shot was fired. And then history struck. On December 7, 1941, the sky over Pearl Harbor exploded in flame. In minutes, the illusion of American isolation vanished. The nation was at war. Factories that once made cars, radios, and refrigerators were converted overnight to produce engines, wings, and propellers. Hamilton Standard became a fortress of industry. Steel arrived by the trainload, oil pumps thundered, assembly lines never stopped. Caldwell's design, once considered too delicate for combat, now had to be produced faster than ever, and with absolute perfection. Any flaw could send a plane spiraling to its death. He worked day and night, reviewing test data, redesigning components for mass production, training new engineers. Every assembly was a battle against time. And across the ocean his invention began to prove itself. The first American fighters arrived in Britain: Curtiss P-40 Warhawks, heavy and rugged, built for punishment. Early versions struggled at high altitude, but with constant speed propellers, they performed like new machines. Pilots reported smoother takeoffs, better climbs, faster dives. The difference was immediate and undeniable. Soon after, the British fitted Hamilton Standard systems to their Spitfires and Hurricanes. The effect was dramatic: shorter takeoff runs, faster acceleration, and greater endurance in combat. For the first time, pilots could push their engines to the limit without fear of blowing them apart. Still, skepticism lingered. In North Africa, under the blazing desert sun, mechanics worried that the fine hydraulic systems would fail under sand and heat. But the propellers held firm, performing flawlessly in the most punishing conditions imaginable. Letters from pilots began to circulate among engineers back home. One read simply: "Your propeller saved my life today. I climbed out of fire and stayed in the air. Tell Mr. Caldwell, it works." Caldwell never wrote back. He didn't have time for gratitude. He only had time to perfect. He studied field reports like scripture. Every vibration, every oil leak, every failure, he treated as a personal challenge. He refused to let any weakness remain. While others celebrated victories, Caldwell planned improvements. He introduced new alloys to reduce weight. He redesigned seals to resist extreme temperatures. He improved the balance of centrifugal governors so that the system responded in fractions of a second. He was no longer building a mechanism. He was building reliability itself. By 1942, the constant-speed propeller was not just a technological innovation, it was an identity. The drone of its precision-filled rhythm became the soundtrack of the Allied air war. B-17 flying fortresses thundered across the Atlantic, their 4 Hamilton Standard propellers synchronized like the heartbeat of an empire. B-24 Liberators carried the same song into the Mediterranean, while P-38 Lightnings with their twin engines and counter-rotating blades, sliced through the Pacific skies like twin lances. Everywhere the Allies flew, the same sound echoed, steady, unyielding, mechanical perfection. Yet even as the world marveled at the machines, few thought of the man behind them. Frank Caldwell remained in Connecticut, working quietly in his office surrounded by blueprints and test data. His war was fought with pencils and calipers, not rifles. But his contribution was no less lethal to the enemy. He followed every battle report, every photograph of aircraft formations over Europe. He read of pilots returning home with damaged wings, missing engines, but propellers still turning, still holding steady. He marked those stories carefully. He was proud but never satisfied. When asked by a journalist what his invention meant to him, he said only, "It means an engine can give all it has, and nothing more. That balance is what keeps men alive." Balance. That was the word that defined his life. As the war intensified, balance became everything, between speed and drag, power and restraint, ambition and caution. Caldwell understood that every advance carried risk, and that even perfection, once achieved, must be protected. He began experimenting with new materials, duralumin, magnesium and advanced steel alloys, to push the limits of strength-to-weight ratios. He predicted that future propellers would be lighter, faster, even more intelligent in their automatic control. He was already dreaming beyond the war. But the war still had lessons to teach him. In the spring of 1942, an Air Corps test pilot experienced a catastrophic oil loss mid-flight. The governor jammed. The propeller oversped. The engine tore itself apart before the pilot could react. He barely escaped alive. The failure haunted Caldwell. For weeks he barely slept. He re-examined every drawing, every part, determined to find the flaw. When he finally did, it was almost invisible, a microscopic crack in a single valve housing caused by a manufacturing shortcut. He redesigned the component personally. From that day on, every part that left the Hamilton plant carried his signature in its precision. By late 1942, no one questioned the constant-speed propeller anymore. It was no longer an experiment, no longer a risk. It was a standard, as vital as armor, as trusted as a compass. And yet, despite its widespread success, Caldwell remained a mystery to most. He didn't give interviews. He didn't pose for photographs. He believed the machines should speak for themselves. He once told a colleague, "If a propeller spins perfectly, it will never be noticed. That's how I know I've done my job." Thousands of pilots would owe their lives to that unseen perfection. In the skies above Europe and the Pacific, the balance he had built, between air and engine, between chaos and control, became the thin line between life and death. And as 1942 turned into 1943, Frank W. Caldwell's creation was about to meet its greatest test yet, the moment when air supremacy would decide the fate of nations. The world was racing toward its turning point, and at the center of it all, one man's impossible dream was spinning faster than ever. By 1943, the air itself had become a battlefield. From the Pacific to the North Atlantic, from the burning fields of France to the frozen skies of Germany, the Second World War was now a war of altitude, a war of engines, fuel, and endurance. Victory no longer belonged only to the bravest men. It belonged to the most efficient machines. At 25,000 feet, where temperatures dropped below freezing and the air thinned to a whisper, a pilot's life depended on the perfect rhythm between engine and propeller. A single surge, a single overspeed could mean explosion. A single stall, and the plane would plummet from the heavens like a stone. But with the constant-speed propeller, that balance was finally under control. American bombers, the B-17 Flying Fortress and the B-24 Liberator, carried the heartbeat of Caldwell's invention on every mission. Their four synchronized propellers kept steady revolutions through storm, flak, and ice. They climbed higher, flew farther, and carried heavier loads than any design before them. To the men inside those bombers, the steady drone of engines was more than sound. It was reassurance, the proof that the machine was still alive, that the system was still holding. In the chaos of combat, that consistency became the sound of survival. On the ground, Caldwell followed every report. He read about missions over Bremen, Cologne, and Schweinfurt, names that filled the headlines with loss and courage. He studied the data, the fuel curves, the altitude logs, the engine failures that weren't supposed to happen. Every detail mattered. Every statistic was personal. He knew the propellers worked. But he also knew that in war, perfection was never permanent. In early 1943, the U.S. Army Air Forces demanded even greater efficiency. Aircraft were flying longer missions, deeper into enemy territory. Engines were being pushed beyond their limits. Caldwell responded the only way he knew how, by refining again. He redesigned the governor system with tighter seals, smoother bearings, and improved hydraulic channels. The new model, the hydromatic constant-speed propeller, became a masterpiece of mechanical precision. It adjusted pitch not just automatically, but seamlessly, anticipating changes in airflow with near sentience. Every fraction of a degree mattered. Every revolution counted. The hydromatic allowed pilots to climb faster at takeoff, maintain optimal speed in cruise, and dive without overspeeding. It gave them control over chaos, not through brute force but through balance. The P-51 Mustang. When the first Mustangs reached Britain, they were sleek, agile, but limited. Their early Allison engines performed poorly above 15,000 feet. British engineers replaced them with Rolls-Royce Merlin engines, and paired them with Hamilton Standard's constant-speed propellers. The result was transformation. At high altitude, where German fighters once ruled, the new P-51s surged ahead effortlessly. Their engines purred at perfect revolutions, their propellers slicing the air with surgical precision. They could climb to intercept at record speed, chase Messerschmitts through the clouds, and escort bombers deep into enemy skies, all the way to Berlin and back. That was the moment the balance of air power shifted. German pilots began reporting a new kind of enemy, one that seemed tireless, one that never lost speed. "They come from nowhere," one Luftwaffe ace wrote. "Always from above, always too fast." It wasn't magic. It was mechanics. Caldwell's creation had become the quiet equalizer, invisible, uncelebrated, but decisive. And yet, even as the world soared on his design, Caldwell remained grounded, literally and figuratively. He stayed in Connecticut, leading a team of engineers who were now producing over 100,000 propeller systems a year. His life was reduced to blueprints and factory floors, calculations and letters. The war raged continents away, but he felt it in every vibration of every engine. He was not a soldier, but he carried the weight of one. One night in 1943, after receiving reports of an entire bomber group lost over Regensburg, he didn't speak for hours. A colleague found him staring at a drawing on his desk, a cross-section of a propeller hub. "They trusted this," Caldwell murmured. "They trusted what we built." He wasn't thinking about glory. He was thinking about responsibility. The government eventually recognized his contribution with awards, the Collier Trophy, the highest honor in American aviation. But Caldwell declined the spotlight. He sent his chief engineer in his place. "It's not one man's invention," he said. "It's a chain of minds." But deep down he knew the truth. No one else had believed in that chain until he forged it. By late 1943, the war machine was unstoppable. Allied aircraft filled the skies by the tens of thousands. Hamilton Standard's propellers powered everything from fighters to transports, from carrier-based torpedo planes to reconnaissance craft. Everywhere the same metallic rhythm, the same heartbeat of engineering. Yet as the Allies gained momentum, Caldwell faced new challenges. The increasing power of aircraft engines, now exceeding 2,000 horsepower, introduced vibrations that threatened to tear even the best designs apart. He returned to the test rigs, adjusting damping systems, experimenting with blade flexibility and new alloys. Each improvement cost time. But time was measured in lives. He worked without rest. His notes from 1944 are filled with single-line entries: redesign successful, bearing stabilized, blade resonance reduced. Each phrase reads like a heartbeat, steady, methodical, relentless. And outside, the war reached its crescendo. In Europe, bombers darkened the sky over Berlin. In the Pacific, American fighters swept across island chains under fire from below. Every mission depended on the same principle: maintain power, maintain speed, maintain control. One pilot, returning from a mission over the Marianas, later said, "You could feel it, the propeller thinking with you. You pushed the throttle and it answered like it knew what you needed." That sense of trust, man and machine, mind and mechanism, was what Caldwell had always dreamed of. But there was one test he could never control: time. In early 1945, as Allied forces closed in on victory, Caldwell's health began to decline. Years of exhaustion and relentless precision had taken their toll. He rarely left his office, and even when he did, he carried notebooks everywhere filled with sketches of future designs: adjustable pitch blades for jets, composite materials, fully automated governors. He was thinking beyond propellers, beyond even the war. He was thinking about the next generation of flight. When Germany finally surrendered in May 1945, the world celebrated in the streets. Caldwell didn't. He simply sat in silence as the news came through, staring at the blueprint that had started it all. The war was over, and so was the age of the propeller. Jet engines were already rising. Their roar would soon replace the steady hum that had defined the skies for half a century. But for one moment, that brief window between the age of wind and the age of fire, Caldwell's creation had ruled the air. He never claimed victory. He never called himself a hero. He once told a reporter who tracked him down, "A propeller isn't a weapon. It's a promise that energy can be used wisely. The world will forget the name, but it will remember the balance." He was right. By the end of the war, Hamilton Standard had built more than 500,000 constant-speed propellers. Nearly every American aircraft that flew in combat used his system. And though the age of jets would soon dawn, Caldwell's principles lived on. In every governor, every turbine, every control system that sought equilibrium between man and machine. In an era defined by destruction, his invention had been one of creation. Proof that precision could be a form of mercy. Looking back now, it's easy to see numbers: miles per hour, climb rates, production totals. But what those numbers don't show is the invisible thread that tied all of it together: one man's refusal to accept limits. How many times in history has progress depended on someone who simply refused to hear the word impossible? Frank W. Caldwell never went to war. He never fired a weapon. Yet his work decided battles fought by men he would never meet, in skies he would never see. He built a mind for machines, and in doing so, gave wings to humanity's greatest struggle for mastery over nature itself. As 1945 faded into peace, the sound of his propellers slowly gave way to the roar of jets. But for those who remembered, that steady hum, that constant, unwavering rhythm, was more than a sound. It was a memory, a heartbeat, a legacy spinning forever in the wind. When the war ended, the sky fell silent. After years of thunder and fire, the world woke to a strange peace, the kind that feels too quiet, too wide. Airfields once alive with the constant hum of engines now lay still, littered with empty shells and faded insignias. The great flying machines of war, the fortresses, the lightnings, the Mustangs, were grounded one by one. Some were dismantled, others sold for scrap, their metal melted into the foundations of the post-war world. But for Frank Caldwell, silence was never peace. He had spent his life listening to the language of motion, the pulse of pistons, the whisper of air over blades. And now, as the age of jets began, that language was dying. In 1946, he walked through the Hamilton Standard plant for what felt like the last time. The war contracts were gone, replaced by peacetime austerity. Rows of idle machines stood like monuments to another era. Engineers who had once built weapons of precision now designed propellers for commercial transports, agricultural planes, or small civilian aircraft. The world had moved on. Jet propulsion, fast, sleek, unstoppable, had become the new obsession. Engineers in Britain and Germany had proven that the turbine engine could push aircraft beyond the limits of propeller-driven flight. For the first time, airspeed was not bound by the shape of a blade. Caldwell admired the elegance of the idea, but part of him grieved. He had spent 2 decades chasing balance, teaching air and metal to cooperate. The jet replaced that harmony with raw force. It was magnificent, but it was also brutal. He once told a young engineer, The propeller sings. The jet shouts. In a few short years his life's work, the system that had carried nations to victory, was becoming obsolete. Still Caldwell did not stop. He continued at Hamilton Standard, now turning his attention to propeller design for transport and research aircraft. His focus shifted from power to efficiency, from war to peace. He envisioned propellers that could operate quietly, economically, and last longer than ever before. He studied new materials, lightweight composites, hollow-core blades, anti-icing systems. He predicted that while jets would dominate high-speed flight, propellers would remain vital for endurance and versatility. The future, he wrote in a 1947 paper, belongs not to a single idea, but to adaptation. Adaptation, the same principle that had guided his invention in the first place. But history is not kind to the quiet. By the early 1950s, aviation textbooks devoted only a few paragraphs to constant speed systems. The names of new heroes filled the headlines: von Ohain, Whittle, Boeing, Lockheed. Jet age pioneers. Frank Caldwell's name faded into the footnotes. He didn't complain. He didn't chase credit. He continued to teach, mentor, and refine. When asked once if he resented being forgotten, he smiled faintly and said, "The pilots remember. That's enough." And indeed some did. At reunions and memorials, veterans who had flown over Europe and the Pacific often spoke of the sound that had carried them through the war. They described that steady rhythm, the hum of constant speed props, as the sound of survival. For them, that sound was Frank Caldwell. In 1949, Hamilton Standard held a small ceremony to honor him for his wartime contributions. He stood before a modest crowd of colleagues and officials, holding a plaque engraved with his name. There were no cameras, no press, no fanfare. He thanked them quietly, then returned to his office. On his desk that night was a drawing, his first sketch from 1931, the seed of everything. The paper had yellowed, but the lines were still sharp, deliberate, confident. He traced the edges with his fingertip and whispered, "You flew." Outside, the wind moved through the trees, a soft echo of the sound that had once filled the world. But history, as always, kept moving forward. By the mid-1950s, commercial aviation had entered the jet age. The Boeing 707, the de Havilland Comet, the Douglas DC-8, all screamed across the stratosphere at speeds Caldwell's propellers could never reach. Passengers marveled at the quiet cabins and short travel times, never knowing the decades of struggle that had brought them to that point. Yet even in the new era, traces of Caldwell's genius endured. Turboprop engines, hybrids between piston and jet, still relied on the same constant speed principles he had perfected. Cargo planes, naval patrol aircraft, and small airliners carried his legacy high above oceans and continents. His invention refused to die. It had simply evolved. Still, as his body aged, Caldwell began to reflect on what it all meant. The medals, the patents, the papers, they felt distant, almost irrelevant. What mattered was that, for a brief moment in time, he had given the world something pure, the union of thought and motion. He often sat by the window of his modest home in Connecticut, listening to the faint drone of aircraft passing overhead. He could tell by the sound alone whether it was a propeller or a jet. The jets moved too fast, their noise fading before their presence could be felt. But when a propeller passed, he smiled. "That one breathes," he would say softly. He believed machines had souls, not in the mystical sense but in the way they carried the intentions of their makers. A careless design produced chaos. A balanced design carried grace. His propeller, he thought, had both survived and transcended him because it was born from that balance. In 1954, the Smithsonian Institution requested one of the original Hamilton Standard constant speed units for display. Caldwell attended the installation quietly, standing among tourists who didn't recognize him. He watched as a curator described the device as a milestone of mechanical innovation that helped win the war. He didn't correct him. He just nodded. The guide moved on, the crowd dispersed, and Caldwell lingered for a moment, alone before the glass case. His reflection hovered beside the polished aluminum blades. For an instant he imagined them spinning again, the vibration through the air, the resonance of motion, the song of engineering. He closed his eyes. The sound filled his mind once more, the echo of 1943, of engines roaring above Europe, of a sky alive with purpose. That was enough. He retired a few years later, though he never truly stopped working. He continued consulting for Hamilton Standard, quietly advising younger engineers who would go on to design the next generation of flight systems. Many didn't even know who he was. But history has a way of circling back. In the late 1950s, as the space race began, engineers at NASA revisited Caldwell's Governor designs while developing early turboprop and rocket fuel systems. His principles of self-regulation and feedback control were cited as foundational, the same balance of force and resistance, input and correction, that allowed machines to maintain stability in unpredictable conditions. Caldwell lived long enough to see that echo. He never claimed it as his legacy, but it was. He once wrote in a letter to a colleague, "A machine should not only move, it should understand why it moves." That's where precision becomes art. By the time he passed away in the early 1960s, his name had faded from public memory. There were no front-page obituaries, no televised tributes. Only a few paragraphs in an engineering journal, summarizing a lifetime in a few sentences. But his invention, the impossible propeller, still spun on across oceans, across decades, across every sky where balance mattered more than power. Even now, when a small aircraft lifts into the morning air, its propeller adjusting automatically to climb through the wind, a fragment of Caldwell's genius lives within it. He never asked to be remembered. He only asked for things to work. And in the quiet hum of a modern engine, somewhere between the past and the present, that wish still holds true. Because some revolutions never stop. Time moves forward, but the air remembers. Even now, when the propellers of modern aircraft turn in quiet synchronization, they trace the same invisible geometry that Frank Caldwell first imagined nearly a century ago. The same laws of balance, the same promise of control, the same pursuit of perfection. History, for all its noise, is often shaped by silence, by the men and women who build rather than boast, who create not for glory but for necessity. Caldwell was one of them. He never led armies or signed treaties. He didn't stand in front of cameras or command headlines. But in the fragile space between power and precision, he built something that endured. When engineers look back now, they see more than just an invention. They see a philosophy. Caldwell's constant-speed propeller was more than a mechanism. It was a message that true mastery of technology lies not in domination but in harmony. It taught aircraft to adjust, to listen to the air, to adapt instead of resist. In an age of destruction, that lesson was quietly revolutionary. And perhaps that is why his story still matters. Because we live in another age of acceleration. The machines are faster, smarter, more autonomous than ever. We've traded blades for algorithms, hydraulics for silicon. But the question remains the same: how do we balance progress with control? Caldwell's answer still echoes through time: find equilibrium and you find survival. His invention was born from that principle. Each blade, each piston, each valve was a compromise made perfect. It was engineering as empathy, a design that understood the limits of both man and machine. It is easy now to overlook such ideas. We speak of revolutions in digital code, of artificial intelligence and quantum leaps. But before any of that, there was a man with a pencil, a desk, and a belief that precision could be merciful. That belief carried thousands of pilots through the war. It carried nations through the sky. And long after the sound of his propellers faded, it carried humanity toward a new frontier of thought, where machines could sense, adjust, and protect. Frank Caldwell never saw himself as a visionary. He saw himself as a listener, to air, to motion, to the unspoken language of mechanics. He once said, "Air is the most honest critic. It tells you immediately when you're wrong." That humility was his genius. When he died, there was no great memorial, no museum built in his honor. But his work never stopped speaking. Every aircraft that rises with an automatic pitch control, every wind turbine that adjusts its blades to catch the shifting breeze, every drone that stabilizes midair, they all whisper his name, even if the world has forgotten it. Because every one of them carries the same idea: self-correction, the ability to adapt, the intelligence to survive change. And perhaps that is the greatest legacy of all: not fame, not wealth, but influence so deeply woven into the world that it becomes invisible. We tend to remember the pilots, the daring, the brave, the ones who touched the edge of the sky. But behind every flight, there is an unseen engineer, someone who imagined the impossible and made it work. Caldwell was their voice, quiet, deliberate, unyielding. He proved that revolution does not always come from noise or chaos. Sometimes it comes from balance. In the archives of Hamilton Standard, his notes still exist. Thousands of pages of equations, sketches, and small observations written in careful ink. Some pages contain no numbers at all, only thoughts. On one, dated 1942, he wrote, "We are not building machines. We are building trust. Trust, between metal and motion, between invention and instinct, between man and the sky. That trust defined an era. During the war, the pilots who soared through fire trusted that their engines would hold, that their propellers would not fail. And that trust, invisible yet absolute, allowed them to fight, to live, to return. It's easy to measure a weapon's impact in speed or range or kills. But how do you measure the power of something that gave men confidence to face death? How do you count the lives saved because an engine didn't fail, because a machine understood when to ease and when to push? Those numbers don't exist. But their echoes do, in the generations that followed, in the engineers who inherited that same hunger for precision. When the jet age dawned, Caldwell's ideas didn't vanish. They evolved. The principles of constant speed, of adaptive control, became the foundation for turbine governors, feedback systems, even spaceflight stabilization. The Apollo spacecraft, decades later, would rely on systems that traced their ancestry back to the same mechanical logic he perfected. Balance had become universal. And perhaps that is why his story deserves to be told, not as nostalgia but as reminder. In every era, there are ideas the world calls impossible. Ideas too complex, too fragile, too ahead of their time. Caldwell's life proves that those ideas are worth pursuing, not because they guarantee success but because they demand belief. Belief in the unseen. In the long chain of history, his contribution may seem small, a mechanism of gears and oil, forgotten amid the noise of war and progress. But when we listen closely, we can still hear it, the steady hum of an engine holding its rhythm against the wind. That sound is more than history. It's human. Because behind every machine is a heartbeat, not of metal but of intent. And Frank Caldwell's heartbeat still echoes wherever balance is sought, wherever innovation meets discipline, wherever progress learns to listen. He gave the world something invisible yet enduring, proof that the greatest revolutions are those that work so perfectly, you forget they exist. And maybe that's the point. A perfect invention disappears into the background of history. It becomes part of the world's natural rhythm, unacknowledged but irreplaceable. Caldwell's propeller did just that. It vanished into success. But if you stand on a quiet airfield today and you listen closely as a small aircraft takes off, the hum rising, steady, controlled, you can still hear it. The same balance, the same grace, the same impossible idea brought to life. That sound is the sky remembering. And if you ever wonder what kind of mind it takes to change the world without ever claiming it, remember Frank W. Caldwell, the man who taught machines to breathe. He proved that even in the age of war, there could be beauty in precision. Even in the pursuit of speed, there could be mercy and control. And even when history forgets a name, the air never does. So when you look up and see the faint glint of a propeller catching the sun, remember that what you're hearing is more than metal spinning through air. It's an echo of one idea, one engineer, and one moment in time when the impossible became real. And if stories like this remind you that genius often hides in silence, that the world is built on unseen hands, stay curious, keep listening, and carry these voices forward. Because somewhere, above the noise of progress, the sky is still whispering the name Frank W. Caldwell.